In this video, we're going to take a closer look at the central limit theorem with means. In our last video, we learned that if either the population has a normal distribution or the sampling distribution had samples of size 30 or larger, then the mean of the sampling distribution would take on a normal shape with a mean of mu, which was the same as the population mean, and a standard deviation of sigma, which is the population standard deviation, divided by the square root of n. Now, this new model is a normal model, and that means we can apply what we know already about the normal model. So think back to using Excel and norm dist and norm sdist and all of those things, and finding z-scores and probabilities. Now, before, when we were finding the z-score for a population, we took x, which was our observed value, minus mu, which was the population standard deviation, population mean, divided by sigma, the population standard deviation. So notice everything here has to do with the population. But now we also want to look at what happens for sampling data. So we're still going to use the same basic idea, but notice x is now x bar. Now x bar is just fancy for a mean. So x bar is the mean of the sample. And then mu sub x bar, remember that's what we're expecting. So that is in fact going to be the exact same thing as the mean. And then remember the standard deviation of our sample we said was actually found by taking the standard deviation of the population divided by the square root of n. Once we do that, that's going to affect our z-score, but our probabilities are going to be found the same way that we did previously with all of our other z-scores. So if you still remember how to do all of that, this is going to be a bit of a breeze for you. While we will be using Excel quite extensively throughout the course, I do want to make sure that you are not just randomly plugging things into Excel to find the solution, but actually understanding what we're doing. So we're using Excel as a tool, not as a way to just do it all and not really truly understand anything. So I'm going to look at two questions, one having to do with the population and one having to do with the sample. And I've already worked them out for you, but I just want to talk through them with you so that you understand. So both of these deal with that according to the CDC, the mean total cholesterol level for persons 20 years of age and older in the United States from 2007 to 2010 was 197 milligrams per deciliter. This is considered the population. So that's going to be the mean of our population, or mu. Use a standard deviation of 35 milligrams per deciliter, so that is our standard deviation of our population, and assume the cholesterol levels for the population are normally distributed. That's code for, yes, you can use the central limit theorem because the population is normally distributed. So, the first question deals with the population. Now remember, with the population, I'm using a z-score that includes all the values from the population. So I don't have to worry about, dividing by the square root of n or anything. That's to do with the sample. So in this case, x is going to be the 183. The question asks, what's the probability that I randomly select one adult from the population and that adult has a total cholesterol level of less than 183? So that's my x value. That's what I'm testing. Notice here, I now have 183 minus 197. Remember, if you put that in your calculator, put the parentheses around it. Divided by 35 gives me negative 0.4. And this, the way that I've set that up in Excel is the exact same thing as norm sdist, which is the way that I would do it, negative 0.4, comma 1, or true. Again, we're going less than 183, which means the area to the left. And we know that Excel always calculates the area to the left. So that value is the probability. So it says, what's the probability? And again, we've done this a lot, so hopefully this is all coming back to you. But essentially what we're saying is the probability that the value that we find is less than 183 is the same that the probability that the z-score is less than negative 0.4, and we use Excel to calculate that value. Now, I left this space over here on purpose because I wanted you to get a good picture that for this population, remember the mean is 197, and then we talked about the fact that this is basically 3 standard deviations in each direction. We'll cover most of our data. And the important thing to remember here is that each of these distances is a difference of 0.35. I'm sorry, of 35. 35 milligrams in each direction. So I'd subtract 35 to the left, I'd add it to the right. And the z-score of negative 0.4 tells me that somewhere in here, to the left, negative saying to the left of our mean, is the area that, or the position that I'm looking for, and then we're finding this area. Now, that's going to make sense in a second when we look at a sample and how that's going to be very different. So again, before we look at the sample, what does this value mean? That means that the probability that a randomly selected adult, that one adult from the population will have a cholesterol level of less than 183 is about 34.5%. Now let's take a look at the exact same question, but using a sample instead. And if you'll notice, I'm still using 197 is still mu and 35 is still sigma. But now I have a randomly selected sample instead of population of 150. So I've got this other variable of n, which is 150. And we're asking, again, the exact same value for x, 183. We're saying, what is the probability that the mean will be 183? So this is actually x bar, a mean of 183. So notice that finding the z-score is the same process, except that I'm dividing by, instead of 35, 35 divided by the square root of 150. Now your book doesn't call it this, but it's called, oops, maybe I'll spell it right for you. It's called a standard error. So as I'm showing you this in Excel, I'm going to keep referring to it as standard error, even though your book doesn't call it that. So the standard error is found by taking the standard deviation of the population divided by the square root of n. Remember, we talked about that. In this case, that standard error is about 2.9. Now, the reason that I want to bring that up is, if you'll recall the picture we just made, so this is 197 still in the middle, and when we just did this with the population, we said that this would be 35, adding 35, subtracting 35. So the difference here is, now that we're looking at a sample, we're saying it's not 35 anymore. It's not the standard deviation. Now it's the standard error. So we're saying I would be adding 2.9, not 35, but 2.9, and subtracting 2.9. And so we can see our probability is going to be quite a bit different. When I find a z-score of negative 4.9, that says from the mean, I'm going 4.9 standard deviations to the left. So I'm basically finding this tiny little area down here, which is not very much. As you can see, plugging this into Excel, I'm getting 0.000000479, which is essentially 0. Now, before we continue, let's just always make sure that makes sense. Our question says, what's the probability if we're expecting everybody to have a cholesterol level of 197? What's the probability that I randomly select 150 adults and their average cholesterol is less than 183? Well, it makes perfect sense that this would be a very small value. It's a lot more probable that I would select one person at random and it's 183 or less, as opposed to selecting 150 people and randomly selecting that their average cholesterol would be less than 183. Let's take a look now at how to use Excel to find these values for us. So before I show you how I've set this up, let's go ahead and just find them as we normally would, say in a discussion board post or in a project where we would have to do that all in one cell. For the first question, where I'm dealing with the probability from the population, I would find the z-score by taking the observed value, 183, minus the expected value of 197, which is the mean, divided by the standard deviation of 35. Remember, that does match my z-score. And then I would find the probability of the area to the left, which, if you'll recall, was, if I'm using my z-score, is just norm s dist, and then use the z-score, comma, 1. Remember, norm s dist finds that area to the left. I would do the exact same thing for the other z-score, except I would then divide this by the square root of the sample size, which is, hold on, 150. Sorry, I got lost for a minute. So remember, that is now negative 4.89. That was our z-score. But I'm going to do this the exact same way. Of course, you're going to do that right now. And that's going to be a 9. And again, we end up with that very, very small number. Now, that's all well and good, and it doesn't take that much work. But if I'm doing a lot of certifications, I want to make things easier on myself. And so I'm going to, of course, tell Excel how to do all of this work for me. So for the z-score, I'm going to just set it up using the formula of x bar minus mu divided by, and then open a new parenthesis. And remember, we want the standard error. So you can either create something that says standard error and then point it to that, or you can just say the standard deviation divided by the square root of the sample size. Now, if you're going to use something with a population, use a sample size of 1. So as you can see, this matches the negative 0.4 that I found by hand. And if I change the sample size to 150, it matches the z-score that I found. Now, in terms of finding the, I'm going to go ahead and change that back to 1. In terms of finding the value less than, I'm just going to use norm s dist, just as I did before, and I'm going to use the z-score placeholder, comma, 1 for true, because less than is always going to be to the left. So again, for my first value, that does match what I found for probability. And if I change this to 150, then I essentially get 0, which is what we talked about before. Let's look at another question now, still using the central limit theorem for means, but now we're looking at greater than. So I have the elevators are required to have weight capacities posted if the weights of U.S. men are normally distributed. So stop right there. It just said that the weights of U.S. men are normally distributed. So when you see that, you should in your head be thinking, great, the population is normally distributed. Yes, I can use the central limit theorem. So check for step 1. We're already done. The mean of U.S. men, of weights of U.S. men, 194.7 with the standard deviation of 32. And these are in pounds. What is the probability that a random group of 10 men, so again, stop right there, a group of 10 men tells me this is not a population, this is a sample of 10 men. So the sample of 10 men who enter an elevator will have a combined weight greater than the weight capacity of 2,000 pounds posted in the elevator. So step 1, yes, I can use the central limit theorem. The population is normally distributed. Step 2, draw the curve. Typically, I don't do that. But what you should be thinking about is what's the mean, 194.7, and then what's the standard deviation? And if you'll recall, the standard deviation isn't 32. It's 32 divided by the square root of 10. So some people like to use something here that says standard error. And the standard error would be the sigma divided by, sigma divided by the square root of the sample size. Now, we didn't do that before because if you'll recall up here, we included B3, which is sigma divided by the square root of the sample size. So we're already taking that into account in the z-score. So either way you do it is fine. Now, I did throw a little bit of extra fun in on this one, and that is when we're finding the z-score. So the z-score is found by taking the observed value, which is essentially 2,000. So let me put a parenthesis around that. And then minus the mean, 194.7. But it's really not going to be 2,000 because we expect 10 men to have a weight of 2,000, which means we're expecting each man to have an average weight of 200 pounds. So if you'll notice here, I've already sort of cheated and put in the 200. And then, of course, I would take that divided by, because we're dealing with a group, a sample, I wouldn't divide it by 32. I would divide it by 32 divided by the square root of the sample size, which is 10. And so that would give me, oops, I did something wrong. Hold on. I forgot to change the 2,000 to 200. And so now that gives me the z-score of 0.5235 and so on. Now, that's the same z-score that I got here, again, because I'd already set it up to find the z-score. Now I have to look at the probability. When we're doing questions dealing with greater than, if you'll recall, Excel only calculates less than. So for greater than, I'm going to use 1 minus norm S dist, and then the z-score, and then cumulative. And that's going to give me my solution. And again, I can do the same thing here in a general way and say 1 minus norm S dist of whatever we find our z-score to be, comma 1. Now, before we continue and look at differs by more and differs by less, I do want to point out that other way that we talked about how to find the probability where we didn't have to find the z-score and why sometimes that throws students off. So remember, I can say 1 minus, and instead of norm S dist, I can use norm dist, and I can use the mean of, the x value of 200, the mean of 194.7, and then a lot of students then use the standard deviation and cumulative, and then they say, well, that must be my probability. And notice that does not match the probability that we found. And that's because, of course, I used the standard deviation and I need to use the standard error. So I either need to point it to the standard error cell that I've created, or as I'm doing this, I would do 32 divided by the square root of 10. Either way, it's going to give you the correct answer. But again, you have to be smarter than Excel, so you have to know what to plug in to find the correct solution. So to this point, we've made it through less thans, which is norm S dist of the z-score, and more thans, which is 1 minus norm S dist of the z-score. Now let's take a look at a differs by less and a differs by more question. And again, I always find it helpful to take a look at the picture in these. So on all of them I say draw the curve, but I really haven't drawn the curve because I can visualize it in my head. But as you get to differs by less or differs by more, it might be helpful to draw the curve. So first of all, we're looking at prices of athletic shoes. We're looking at a sample size of 50. So yes, I can use the central limit theorem. And I'm drawing the curve. And again, I want to think about the fact that the center of the curve is 75.15 and that the standard deviation is 17.89. But again, the curve, it wouldn't be 17.89 because it would really be the standard error. So again, if you want to add back in that standard error, which is the standard deviation divided by the square root of the sample size, that gives you a better picture perhaps. So 2.53 would be every time I draw a bar, that's $2.53. So when I'm looking now at the question that says, what's the probability that the price the mean price will differ from the population by less than $5. So it's about 2 standard deviations is what we're looking at. So I want to find this area here in the middle. Now there's different ways that you can do this. And so by all means, the way that I'm going to show you is not the only way, but it's the way that I'm going to show you. So you can do it this way, or you can work it out on your own and find your own way. What I'm going to do is think about the fact that if I'm looking at differ from the population mean by less than $5, that this raw score over here is $70.15, because that would be $5 less than, and this value over here would be $80.15. Now what I want to do is I'm going to find this area. I'm going to find the area to the left of the lower value. And if you'll recall, that's the same as this area. So what I'm going to do is I'm going to find this area, or this probability. That was horrible handwriting. I'm going to find this area and take it times 2, because that's going to give me all of the area that I have now shaded in black. And I'm going to subtract it from 1, because that's going to be what's left over. Because if you'll recall, the entire curve is 1. So there's different ways that you can do this in terms of your spreadsheet. So if I want to say differs by less, my observed value here, I have to calculate the 70.15 myself, which is fine. It's not difficult to do that. So my observed value is 70.15. For differs by less, I'm then going to do exactly what we just said, which is to take 1 minus, and then I'm going to take 2 times, and I'm going to find the area to the left of 70.5, which my z-score is negative 1.98. So I'm going to use norm S dist, and then my z-score, comma 1. And that makes perfect sense that it would be about 95, because if you'll remember, the empirical rule said 68, 95, 99.7. And so that makes sense that this area, which is about 2 standard deviations, would be about 95.19%. Let's look at one last question here, and this is going to be differing by more than. So again, I'm not going to be very specific or precise with my picture, but if I'm looking at a differs by more than, then I'm looking at some value here that this part is okay, and anything that differs by more than that, which is out here, is the area that I need to find. So on the last question, we found the area on the inside, and in this question, we're looking at the area in the tails. So same idea, but when we differed by less, we took 1 minus 2 times norm S dist, and that means here we're just going to not take the 1 minus. We're just going to find this area plus this area, and those 2 areas are the same. So let's take a look at how we would do it. Mean 1.625 inches, standard deviation 0.01. Make sure that you get the 0.01 and not 0.1. Sample size is 50. Observed value, again, this is where you have to kind of do the math. So the easiest way to do it is to take the 1.625, and remember, I'm going to subtract the 0.004 because I want the area on the left. So this is 1.621. Now you can do that in your head as well, but if you make mathematical errors, then the whole thing's wrong. So use Excel for anything that you need it for. Now, again, differs by more. So all I'm going to do is I'm going to find the area to the left of 1.621 and then double it, because that's going to give me this area on the right as well. So just like I did on differs by less, I'm going to take 2 times norm S dist of my z-score, comma 1. And again, differs by more than is that very, very small value. That's all I have for this video. We're going to move on now and look at the central limit theorem with proportions. But again, we looked at one question for each of the directions. And remember, there's different ways that you can set up your Excel worksheet to do exactly what we just did. So if you're doing something differently but getting the same responses, that's just fine too.